Okay guys, now that we have learned on how to conduct partial derivative, the next thing to do is to see on what can we use the partial derivative for. So we can use it first for finding a small increment, and we're also able to find the rate of change using a partial derivative. By the way, we have already covered rate of change before, which involves chain rule in the previous topic of differentiation. However, we have it again here because, as you can see later, this part talk about the rate of change of a functions that have several variables inside it. Right? As you can see here, we have x1, x2 until xn inside one function. Okay, but for our syllabus, we just will be covering just maybe 2 or 3 functions. So we have x, y, or x, y, z. All right, so let's see. The notation for small increment is delta. So let's say we have function z equal to this functions where you have several variables inside it, and the small increment of this function z will be denoted as delta z, and is given by delta z equal to the partial derivative of z over the first in terms of the first variable x1 times with the small increment of that variable, right? And then plus with again the partial derivative of the next variable times with the small increment of that variable. So we will sum all of them to get the small increment of the whole function, right? So next we have rate of change, right? As I said before, in differentiation, we talk about this, right? We find the rate of change by using chain rule. You can imagine that the first part of this formula. So to find the derivative of z in terms of t, we are going to find z over the variable times with the variable over t. So that is what we did before in differentiation. As for now, as you can see, the basic or the core idea is the same, but we sum with several other multiplication because we have several variables inside it, right? So we have the calculation for x1, the calculation for x2, the calculation for x3, or maybe we can say that the calculation for x, the calculation for y, the calculation for z, and we need to sum of them to get the total rate of change, right? So without further ado, let's look at the exercise. Okay, exercise 5.2. We have here a cylinder. Okay, a cylinder. The radius of a cylinder, denoted as r, is increasing at the rate of 0.2 cm per second. You can imagine that the radius of a cylinder, right, is increasing at the rate of 0.2 cm per second, or we can say that the diameter is increasing at 0.4, right, times 2 per second, and the height of that cylinder increasing at 0.5 cm per second. So both of these components increasing, right, in seconds. So now what will happen next? Just imagine you have a cylinder. What will happen to the volume? It will also change, of course, right? So they want to know what is the rate of change for the volume of that cylinder when r is equal to 8 cm and the height is equal to 12 cm. So we are going to find the rate of change by using the formula of rate of change or chain rule that we have looked before previously. And before we do any calculation, let's try to look at some expectation. What do you expect to be happening to the volume? Right? The answers say here, the volume of the cylinder increases. Of course, we'll know that because of the height is increasing and the radius, the diameter is increasing. Of course, when the volume will also increasing, but by how much? So by the calculation of rate of change, we will know that later. The volume will increase by 70.4 pi centimeter cube per second. So in seconds, the volume will increase by this amount in seconds. Alright, so let's see on how to find this answer. Okay, first, of course, we are going to extract out all of the available information so that it will be easier for us to solve it later. So we have 0.2 here. It talks about the radius at the rate of 0.2 centimeter per second. Centimeter here is the radius and second here is the time, so the rdt, and h here is increasing at 0.5 centimeter per second. The cm here is the height and centimeter here is second here is the time, so the hdt. And they want us to find the rate of change of the volumes, hence it is dv over dt. Okay, when r is 8 and h is 12, so r8 h12, and we have a cylinder here, so the formula of cylinder is this, right? So if we are using the idea of chain rule that we have learned before in differentiation, we know that to find dv over dt, we will need to look for dv over something, right, times with something over dt, hence we get dv over dt. So to look at this something, we'll need to look at the available information. As for this, that is in our previous topics, right? For this case, we are talking about a formula of functions that contain more than one variable. We have r and h in one functions here. So of course, to find the rate of change that also involve two variables, we'll need to expand this idea, right? So we need to add not just one component of dv dt, we need to add two components. So one will be with respect to the radius and the other will be with respect to the height. So we have this. Okay, so this dv dt consists of the partial derivative of v in terms of r times with dr dt, right? So we'll get dv dt, and then we also have the same component in terms of height. So why do we do partial derivative here? Because as you can see, we can to find the derivative in terms of r, we need to partially derive it in terms of r. Right, to get it in terms of h, we need to partially derive it in terms of h, because we have two variables here. So we already have this information, right, given in the question, which is 8 and 12 there. Sorry, not 8 and 12. We have 0.2 and 0.5 here. So we'll to find the rate of change of dv dt, we'll need to find the partial derivative of volume in terms of r and h. So by using this function, we derive it. Okay, sorry, this is the wrong term, the wrong notation. All right, the partial derivative of v in terms of r and in terms of h. So if we conduct the partial derivative in terms of r, right, h here will become a constant with pi. Pull it out, r squared will become 2r. So we get 2 pi rh. As for the partial derivative in terms of h, r squared will become a constant with pi. So h will be derived. So it become 1, so we'll get it as pi r squared. So now we have this information, we just substitute it in our chain rule, right? So just simplify it, simplify and then substitute the information of r and h that you have before, which is this, into the chain rule, and you will get this answer. So that is how you calculate for the rate of change. Now let's look on how to calculate for small increment. So for this second question, it talks about the the increment, right? Measurement of a closed rectangular box, length x 5, y 3, and z 3.5, and the possible error of plus minus 1/10, 0.1 centimeter in each measurement, right? It's a possible error, right? The tolerance of each measurement here is 0.1 centimeter. What is the maximum possible error in the calculated value of the volume? So basically what the question asks is, the possible error to be happen here is it might go from plus minus 0.1 centimeter for each of this measurement. So let's say that they want to find the maximum possible error. What is the biggest box that it can produce, right? So should be plus 0.1 centimeter. So the area or the volume and surface here later will be calculated based on this is 5 point actually this is in meter, right? Meter. So basically 500. So 500 plus 0.1, 300 plus 0.1, and 350 plus 0.1, and we look for the total volume, right, of the increment, small increment. Okay, so let's do that. Of course, the first thing to do is to extract all of the information. We have x, y, z here, and I already converted in centimeter because of the measurement here later will be in centimeter. Let's standardize it. So the increment of each of the measurement as being said by in the question is 1/10 centimeter. So the small increment in x is actually equal to y equal to z, which is 0.1 centimeter. To find the volume, we'll use the formula of volume. Formula of volume for a rectangular box is x times y times z. And the formula for increment is this, right? We have the partial derivative of v over x, partial derivative of v over y, and z. Right? We multiply each of them with their respected small increment. So first we look for these partial derivatives, and this is what I get. So yz, so I just multiply so the small increment of x is equal to yz. Sorry, the partial derivative of x is equal to yz. So I substitute y and z, I get this amount. The same goes for the other two. Right? I conduct a partial derivative in terms of y and z to get this, and substitute it to get the formula. So that will represent all of this partial derivative. And next we just simply multiply it with the small increment, and that will give us the answer of this. This will be the small increments in terms of volume. Next they want us to look in terms of area. So in terms of surface, sorry. So to calculate the surface of rectangle, the rectangular box, this is the formula. And we do the same things again, which is we'll need to look for the partial derivative in terms of x, y, and z, right? So partial derivative of x is this. Substitute the formula, the information of x and y and z here to get this answer, and the same goes for the other two. I'll get this, substitute it in the formula of small increment, and time each of them with their own increment to get this. And notice that I use the scale accordingly. When it talk about volume, I put it the scale in term is actually in cm cube. When it comes to the surface, I put it cm squared. Right? So that is about the small increment and rate of change. Thank you.